This is Unit 7, Video 4. In this video, we will do some calculations with the heating curve using the numbers that we showed you earlier. Now, there are two equations we're going to be using, and the two equations have heat equaling something. Notice both of them have heat equals something. The first equation has heat equaling mass times the specific heat times the change in temperature. We're actually going to be able to call this specific heat. Usually has a C that's used, C or an S. We'll use a C for most of the time. The mass will be M. You'll multiply mass by C, and then the change in T will be delta T. Delta, this is the Greek letter for change. So we'll actually call this the MCAT equation. Heat will equal MCAT. Now what you see is there are three portions of the heating curve where this equation will be used. And those are the three portions that represent the heating of the solid, heating of the liquid, and heating of the gas. In all three portions, remember the temperature is changing, the temperature is going up. So this has a temperature term in it. And you'll multiply that temperature change by the specific heat, which is a constant given for the substance, and then by the amount of mass that you have in that substance. So how hot something gets, or how much heat something requires, depends on how much mass you have. The more mass you have, the more heat you'll have to put in to warm it up. And it depends also on how well the substance absorbs the heat. The better it absorbs, the more heat it needs. And then it also depends on how hot you want it to get. And if you want it to get, pretty hot, you have to put more heat into it. So that makes sense that all these are essentially directly related to how much heat you need for the system. The other equation simply has the moles multiplied by heat of vaporization or heat of fusion. Let me make this in. So moles times, we'll do this heat of vaporization. Now heat of vaporization, if you are vaporizing, if you're on this portion of the heating curve, and then it could be heat of fusion if you are melting, if you're on this portion of the heating curve. Now what you'll see here is this also equals heat. So the amount of heat that it takes to melt something depends on how much moles you have. Obviously the more moles you have, the more heat it'll take, and depends on this number here. This is a constant as well, heat of vaporization, heat of fusion. And this equation is used for the two flat lines, for these two portions of the heating curve. Now, in this case, the temperature is not going up. Remember, we said that the temperature does not go up in a phase change, so you don't have a temperature term here. You don't multiply by degrees Celsius. That won't happen here. Okay. Now, the way to remember this is the equation with three parts. This is this top equation. Represents the three parts of the heating curve that are diagonal. The equation with two parts, just moles and heat of vaporization, represents the portion that has of the heating curve with two parts. And that's how you remember which part to use. Okay, let's go ahead and dive right in, and we will be able to do some calculations. First example asks how much heat is needed to boil 3.4 moles of water. Now the question is, which portion of the heating curve are we going to use? Here's the heating curve of water. And we're boiling, so which portion are we referring to? We are referring to this portion right here. Now that portion is going to use the equation that has moles times heat of vaporization. That was the equation down there. So heat would be moles times heat of vaporization. That's the equation that we're going to use. The heat of vaporization of water was given on the previous two slides, I think, ago, and that was 40.79 kilojoules per mole. That was the heat of vaporization of water. We're going to use this number. So really it's as simple as heat equals moles times heat of vaporization. Our moles in this case is 3.4. Our heat of vaporization, let me put the units in there so you can see the units canceling out nicely. 3.4 moles times heat of vaporization, which was 40.79 kilojoules per mole, and the per mole is there because we want the moles to cancel out, as happens when you do some dimensional analysis. The moles are out, and go and do this in your calculator. 3.4 times 40.79, and you get yourself 139, and which is, we have two sig figs, so really 140, and then kilojoules would be our unit. So it'll take 140 kilojoules if you want to boil 3.4 moles of water. That's quite a bit of heat that you have to put in, and your hot plate will sit there for a while until all this boils out. So that's how you do this first problem here. All right, let's do a similar problem, example 5. How much heat is needed to raise the temperature of 15 grams of water from 15 to 45 degrees Celsius? So we turn back to the heating curve. Here's our heating curve again. Ask yourself, which portion of the heating curve are we on now? Well, we're heating up liquid water. So we're going from 15 to 45 degrees Celsius. So this was, remember, solid, this is a liquid, this is a gas, so we're actually on this portion of the heating curve. And we're going from 15, from about here, if this is 15 degrees Celsius, to about 45 about here, this is 45 degrees Celsius. So it looks like we have to go through this region of the heating curve. So we're essentially just covering this portion right here of the heating curve. Which equation do we use? Well, let's use the equation that has the three parts. Heat was mass times specific heat times change in temperature, or MCAT equation. Remember, the MCAT equation refers to the three diagonal portions of the heating curve. So we're actually going to use this equation. All right. By the way, the specific heat of water, the C, is a constant. That's 4.18 joules per gram degree Celsius. Again, this is a constant, so it'll always be handy. You'll have it. So let's do heat is MCAT. And my mass, in this case, looks like it's 15 grams. My specific heat is the 4.18 joules per gram degree Celsius. My change in temperature would be from 15 to 45. So the delta T would technically be 45 minus 15, which is 30. That's what the delta T is. It's actually the final minus the initial temperature. And since I got 30, I'll put 30 in here, 30 degrees Celsius. We'll say this is exactly 30, put a decimal place there. And what you'll have to do is multiply the numbers. So go ahead and let's grab our calculators and multiply 15 by 4.18 by 30 to give us 1,881. 1,881. So we got two sig figs as before. Let's get this down to 1900. The question is, what are the units? Well, you'll see that the degrees Celsius cancels out, grams cancels out, and we're left with joules. So this would be 1900 joules, which is about 1.9 kilojoules. So 1.9 kilojoules to warm up 15 grams of water by 30 degrees Celsius. So notice we can actually do exact calculations. If you want to warm up this much water, here's how much heat you have to be ready to supply. Now, I should say something I probably didn't mention earlier. Notice that we're using Celsius and not Kelvin in these calculations. And somebody may ask, well, why are we using Celsius? Isn't that not a good scale? And it turns out you could use Kelvin and your answer will be the same. Because this is the change in temperature and not the absolute temperature, the change in temperature in Celsius is the same as the change in temperature in Kelvin. So if you actually convert these to Kelvin, so you add 273 to this, you get 288, and do the same thing to this, and you get 318, 28. Like that. You will see that you still increase by 30 degrees. No. Is that right? So still increase by 18. Much better. You still increase by 30 degrees. Good. So it doesn't matter. Both Kelvin and Celsius, the change is the same. All right. Let's do another problem. Oh, actually, go ahead and pause and try this on your own before we dive into the tougher problem. All right. Let's try this one. Here it says, how much heat does it take to raise 36 grams of ice from negative 15 to 55 degrees Celsius? All right, so now we're actually going to do a multiple step problem. Back to the heating curve. Here is our heating curve for water. And it looks like we have 36 grams of it, and let's see what we're going. We've got ice. Negative 15 degrees Celsius, that would put us in the ice category, so like something down here. We're going to begin right down here. This is negative 15. Nice and cold ice. We're going to end up at 55 degrees Celsius, which is liquid, right about here. So 55 degrees Celsius. And it looks like we're going to have to go through three portions of the heating curve. So this portion, and this portion. So let's call this Part B, and Part C. This would be a three-part problem, A, B, and C. Now, in the case of our equations, we're going to use the equation down here. We're going to use the heat equals moles times heat of fusion equation, because we're melting. And then for A and for C, we're actually going to use the MCAT equation. Heat is going to be MCAT. So we're going to have to use this equation twice and this equation once down here. Okay, so let's go ahead and do it. So for part A, we have ourselves from negative 15 up to 0. Now remember, this is 0 Celsius. So it looks like we're heating ice up from negative 15 up to 0 Celsius. We're going to use the MCAT equation for that. So heat is going to be MCAT. And in this case, the M, the mass, is 36 grams. So we have 36 grams of water. Now the specific heat of ice is given to us here as 2.05 joules per gram degree Celsius, and that's what we're going to use. Now we're using S, you can use S or you can use C for specific heat. So multiply this by 2.05 joules per gram degree Celsius, and then we'll have to multiply by our heat change, now, or temperature change. Now be careful, our temperature change here is actually not the whole temperature change. We're just simply going from negative 15 up to 0. We're simply warming ice up to its melting point. So it's actually going to be the temperature change is actually 15. So if that makes sense, it's 0 minus negative 15 to be precise. And that's how we get 15 degrees Celsius for our temperature change. So we'll do 15 degrees Celsius right here. Okay, go ahead and calculate this out. Let's go and plug this into our calculator. So we got 36 times 2.05 times 15. It looks like I got 1,107 joules. Okay, this is my part A answer. Now in part B, we're going to have to do this portion of the heating curve. We're on part B now, and we're going to use the equation that says moles times heat of fusion. So our heat here will be moles times heat of fusion. Now to get moles, we're given grams. To get moles, we have to convert from grams to moles. Always a fun little problem to do. And so that's easy enough, right? 36 grams. We have water. Ice is still water. So we're actually going to do 18.02 grams in 1 mole, which gives us about 2 moles, and that's, I think, the idea. Let's be a little more specific, and we'll get exactly 1.99, good enough. Let's do 2.00. That looks like it's 2.00 moles. Pretty close. Okay, so that's how many moles we've got. Let's go ahead and do that. So we have 2.00 moles. The heat of fusion is given to us as this number here, 6.03. This is the constant that we'll use, kilojoules per mole. So I'm going to put 6.03 kilojoules per mole. And just multiply those two, and you get 12.06 kilojoules. 12.06 kilojoules. Now notice I'm not rounding any sig figs just yet. I'll do that at the end. Okay, so it looks like we've melted our ice. Now we have to heat it up. We're going to heat it up to 55 Celsius. So now we're going to have to go through this portion. We're back to the MCAT equation. So part C, we'll do heat is MCAT. In this case, the mass is still 36 grams. The C now is different. Every state of water has a different specific heat. So this was for the ice. Now for water, remember, that's the 4.18 joules per gram degree Celsius. I would recommend memorizing this number. It's an important number. And then our temperature change. What's our delta T in this case? Well, we're going from 0 up to 55, so it's actually 55 degrees Celsius. Hopefully that makes sense. All right, let's go ahead and calculate how much this would be. Go ahead and do 36 times 4.18 times 55. And it looks like we get 8,276 joules in this case. Okay, these are the 3 amounts. Now, we want the total heat. So what we'll end up doing is essentially adding these 3 up. We're going to add this number, 1.107, to this number, to this number. Now, we have to make sure we're in the same units. So let's go ahead and convert all of them to kilojoules. This one's already in kilojoules. And to convert to kilojoules, we're simply dividing by 1,000. If you need to see that, 1,007, this is joules. So you go from joules to kilojoules. A kilo means 1,000, so you end up dividing by 1,000. So essentially what we've got here is we've got 1.107 kilojoules. And this here is 8.276 kilojoules. So really what we're doing is we're adding 1.107 kilojoules plus 12.06 kilojoules plus 8.276 kilojoules. We're simply adding them up. It looks like 7 and 6 is 13, 7 and 7 is 14, looks like 2 and 2 is 4, and then 3 and 8 is 11, so 21.443. Now sig figs wise, I think we're down to just 2 sig figs. So really 21 kilojoules is our final answer. So let's do 21 kilojoules is how much it takes if you want to warm ice up from negative 15 Celsius to 55 Celsius as liquid water. So hopefully this one made sense. It was a little more involved, got a bit messy, but hopefully it makes sense. All right, we'll do the last one in video 5.